Yes, you're welcome back. Like I said in the previous video, we were to prove the first mean value theorem and then the generalized first mean value theorem. In this video, we are going to prove the generalized first mean value theorem. Now, here is a theorem. As you can see in the picture, it says that let f and g be continuous real functions on this closed interval AB, such that this is the symbol for such that such that for all, this is a symbol for all or for any, for such that for all x in this interval, we have that the function g we are talking about is non-negative. Non-negative means it is greater than or equal to 0. Then if we have such condition, then there exists, this is a symbol for there exists, then there exists a real number. Let's call the number epsilon. This is the number epsilon. Then there exists a real number epsilon, which is also in this interval, such that this integral holds. That is the integral of the two functions from a to b is equals to a constant. This f of epsilon is a constant. We are taking the function at a particular point, the point you are considering in the interval. So a constant times the integral of g of x dx. This is the statement of the generalized first mean value theorem. Now we are going to prove this theorem. In order to prove this theorem, we are going to invoke some other theorems which will be displayed in subsequent slides. Now let us consider other theorems like this theorem. I call it theorem 1. Now this is the intermediate value theorem, I think. Yes, this is the intermediate value theorem. No, the extreme value theorem. Yes, it's a combination of two theorems here, but it's generally the extreme value theorem. Yes, the extreme value theorem. Now we say let f be a real function which is continuous on the closed interval AB. Now if this is true, if we say you can see this statement here is this word here is very important, continuity. That if x have the property of continuity in a closed interval, then we can say that f is Darboux integrable. Yes, on that interval. What do we mean by that? In essence, we are saying that by the extreme mean value theorem, we are saying that let us consider the points A and B, which is the open interval. I1, I call it I1. It's actually the open interval. So let's consider A and B as members of an open interval, I1. And then let us consider a real number epsilon that lie between the function at these two ends, the function at A and the function at B. Now what do we mean by that? We mean that there is no order here between A and B. We don't know which is larger. A could be larger than B, B could be larger than A. What we know is A and B are in the interval I. Now, if that is true, then epsilon will lie between A and B, either as this or as this. In the first scenario, the function at B is greater than the function at A. In the second scenario, the function at A is greater than the function at B. In both scenarios, epsilon is lying between them. Then if this is true, then there exists a point C also in that open interval. Remember that we are talking about epsilon being a function that lies between two other functions. In this other case, we are talking about a point C that is in that interval. So you should take note, epsilon is a function while C is a point. So we consider a point C in that open interval such that the function at point C, f of C, is equals to this epsilon. So if you pick any point in that interval and then you operate on that point, what you get is epsilon. That is what this statement is talking about, provided epsilon is lying between the function at the two ends of that interval. Then if that is true, then that is the extreme value theorem. Now I think this should be the intermediate value theorem. Yes, it's the intermediate value theorem. It's a mistake. It's the intermediate value theorem. The extreme value theorem is theorem 2. Now, let us look at theorem 2. Theorem 2 says, let f be a real function which is continuous on AB. Then, for any x we choose that is in AB, there exists a point C. Remember, we are always talking about point C. So C is always in that interval. Now, there exists a point C in that interval such that the function at C is always smaller than the function at X. We also know that both X and C are in the interval. So it's like picking 2 points in the closed interval and then operating on those points. And then definitely we are saying that one point is definitely less than or equal to the other points. Good. Now we are saying that C is always less than or equal to X. And then it continues. It's not there. That's why you're seeing the and there. The other part of it says, this first scenario is saying that f of C is less than or equal to X when we have X and C in the interval. The second scenario is also saying that X and C is also in the interval, but in this case, f of C is greater than or equal to f of X. So these are the two statements of this theorem. I think this theorem is the extreme value theorem. The theorem 1 is talking about the intermediate value theorem, while the theorem 2 is the extreme value theorem. Now, we'll use these theorems to prove the generalized first mean value theorem. Now, let us consider an integral. Now, recall that f and g are both continuous. Good. So we have the integral of a continuous function, and then we say let that integral be 0. Now, we also should recall that by the statement of the generalized first mean value theorem, g is non-negative. You can see that this g is non-negative, so it is used in the proof. Now we know that g is non-negative. Hence, by continuity, yes, the continuity of non-negative real functions with 0 integral, g of x is 0. Now, what does this mean? It means that if the whole of this integral is 0, an integral can be 0 if the function itself is 0. So the integral is 0 implies that the function itself is 0. That is the implication of that statement. Then if that is true, then if I are going to substitute g of x as 0 into the original formula, this is the original formula here. We are substituting g of x as 0, so this becomes integral of a to b integral from a to b of f of x multiplied by 0 is equals to f of epsilon of multiplied by the integral of g of x. So g of x will be substituted as 0. So it will be f of epsilon multiplied by the integral from a to b of 0. So you observe that everything on this right hand side is 0. Everything on the left hand side is 0. This proves that 0 is equal to 0, hence the formula is true. We have proved one scenario. Now that is not all. Remember, we are trying to show that g of x, this is, now what does this mean? Sorry, hold on. What does this mean? And what does this mean? Now, this is greater than or equal to 0 mean there are two possibilities. The first possibility is greater than 0. The second possibility is, first is greater than 0. Second possibility is equal to 0. So we have just shown equal to 0. The next one we want to show is what if g of x is greater than 0? That's what we are talking about. So we have just shown that when g of x is 0, the formula holds. Now let us check. Now let g of x not, the integral not be 0. Now let's take the integral, let it not be 0. Let it be something else except 0. Then we know that, we also know that from theorem 1 that f is Darboux integrable. Now let's look at theorem 1. Look at theorem 1. F is a real function which is continuous. I told you about continuity. The fact that f is continuous in the statement of the generalized first means, now they say let f and g be continuous function. The fact that f is continuous here, it means that f is Darboux integrable. And what does it mean for f to be Darboux integrable? F is Darboux integrable if, that is, in that interval AB, we can find a real number that is lying between the two ends, the function at the two ends, such that we can find another real number in that interval such that the function at this second real number C is always equal to the first number we chose. So if we can prove this, if we can use this, then we have shown that f is Darboux integrable. Now let's go back to our proof. Now we know that f is Darboux integrable, that f satisfies these conditions. Then by the extreme value theorem, now let's look at the extreme value theorem. I said the theorem 1 was the intermediate value theorem. Earlier I made a mistake and I said it was the extreme, and then later I told you it was the intermediate value theorem. Then I said theorem 2 is the extreme value theorem. Now by the extreme value theorem, if f is Darboux integrable, yes, then we can find two real numbers in the closed interval such that the function at one is either less than or equal to the other or greater than or equal to the other. That is just it. So let us go back to this. Now we are going to use the extreme value theorem. Now let us pick two real numbers in that interval. Let's call it m and m, small m, big M. Now if by the extreme value theorem we have two real numbers such that the function at the first is less than f of x, and then the function at the second is greater than or equal to f of x. If this is true, then f of x should lie between the small one and the big one. Now what does this statement mean? Now look at the function at small m is smaller than or equal to f of x, and then the function at big M is greater than or equal. That means f of x is definitely bigger than small m and smaller than big M. That is what is written there. So you see that the function f of x is greater than f of small m but less than f of big M. These two statements, this statement and this statement, imply these statements. So they are the same things. So we have used the extreme value theorem here. Now let's see the next slide. Now from this previous slide, what are we doing? We are multiplying this from this inequality. We are going to multiply by g of x. We are going to multiply every term in this inequality by g of x. Okay. Now if we do that, we have that g of x fm is less than fx g of x is less than f capital M g of x. Now if we take the integral, if we integrate this, okay, hold on. If we integrate this from a to b, then we get this line. I believe you can see it. Then now this fm is just a number, it's a constant. It comes out of the integral as this. Capital M2 is a constant, it comes out of the integral. And then we have this. Then let's go to the next slide. Now I'm going to divide through from this, from here. From this, we'll divide everything here by this g of x. So if I divide by g of x, I divide by integral of g of x, integral of g of x, integral of g of x. So what will be left after the division will be this. Fm will be alone, f capital M will be alone. And then we have this. Now, recall theorem 1. Yes, this part is very, very important. Theorem 1. Let's go to theorem 1. Just look at what we have here. We have small fm. We have this integral, this fraction between small fm and big fm. That if this is true, let's go to theorem 1. Now, what does theorem 1 say? Theorem 1 says that if we can find a number, just look at the magic here. If we can find a number, or rather a function, epsilon, that is between two numbers, two ends, the two ends. If this is true, then we can find another number c such that the function at c is equal to epsilon. So take note, epsilon is at the center. C is any real number. The function at c is equal to the value at the center of that inequality. Now let us go back to our proof. Now we have here, we have that this is at the center. We have the two endpoints. Then by theorem 1, that if this is true, then we can find some epsilon. Now epsilon is representing c. In the other, now we are looking in theorem 1, we can find some c, but in this now, it's just a change of notation. We can find some epsilon in that interval such that what is at the center? What do you see at the center? This. Remember, we use what is at the center. So such that the function at epsilon should be equal to the value at the center. And this is the value at the center. So from this, we simplify this and we get this. Now this is the final result for the generalized first mean value theorem. Now we have successfully proved it. You can look at the statement of the theorem and compare it with the final result. Then this is the statement of the theorem, and then this is the final result of the theorem. So we have successfully proved the generalized first mean value theorem. Thank you. Subscribe to my channel. I would really appreciate. Thank you.